Hello, everyone. Okay, so quick lecture video about your guided notes, pages 1 through 5 slides. Okay, so let's look through it, and I want you to take a minute, pause the video if you need to, go grab your notes that you took because we're going to be adding to them, just like we would in class. If I say something that makes more sense, I want you to write it down. If we do a practice problem, add it to your notes. Okay? Okay, so reaction rates. Reaction rates, well, the formal definition is how long does it take for a reaction to complete or a certain amount of product reactants to turn into products. Okay? Because as you know, some reactions go quickly and then some go slowly. So usually combustion reactions will go really quickly, but other reactions like something turning into rust will happen, iron turning into rust will happen very, very slowly over time. Right? And so a reaction rate is how long does it take for all of the reactants to then turn into products? Because you can see after a small amount of time, some of them have turned into products, but how long does it take for the majority or all of them to turn into a product? Okay, so here's how we look at reaction rates. It's a change in, see this delta symbol? This delta means change in reactants to products over the amount of time, the change in time in which that happens. And that's going to be the average of the whole reaction rate. Okay, so the change in the product over the amount of time that it took. So reaction rates are determined experimentally. And it's just when we can analyze how much reactant we have left and how much product we have left and how much time it took to get to that point. They're not calculated from balanced chemical equations. Okay, so it's from measurements in the lab. Right, so what's happening? Well, you know that chemical bonds have to be broken in the reactants and the new bonds have to be formed to create products. Nothing's being created or destroyed. It's still the same atoms. They're just rearranged. But the idea behind this is they cannot break bonds and they cannot form new bonds unless they collide. So if we have molecule A and molecule B, they have to collide in order to form this A-B combination. If they don't collide, then they're never going to have that opportunity. It doesn't just spontaneously happen. A collision does have to occur. Okay? So here's another example with water. If we have hydrogen gas and we have oxygen gas, they have to collide and form what we call this activated complex, which is just that perfect alignment where they're running into, well, where this collision is happening, that we end up with the new product. All right, so if we have carbon monoxide and we have this nitrate gas, this nitrogen dioxide, and we get carbon dioxide and then nitrogen monoxide, what had to happen? Well, this collision had to occur. And it's actually really small number of collisions that do result in the products. But why is it? Why is it that not every single collision results in a new product? These two reactants will collide all the time, but only a fraction of the time will they actually form the product. And the reason for that is the orientation. They not only have to collide, but they have to collide in a perfect way. That collision has to be lined up in the perfect way so that the products can be formed. Okay, so a collision has to happen and the orientation of that collision has to be perfect. Right, so if it was oriented, if the orientation of the collision is the way that it needs to be, then we'll form new products. But if it's not, if they hit in a different way, then it's not going to form the products. Chemistry thought of the day! Have you missed chemistry thought of the day? It's a good one. Don't you love when they involve a cat? Look how cute that little kitty is. Okay, why don't you drink water while studying chemistry? Because you'll dilute your concentration. Because concentration is how much you have, and then if you add water, then there's less in that space. Okay. Chemistry. All right, so what is collision theory? So far we know that molecules have to collide to form new bonds, and they have to have the correct orientation, but there's a third part of this, and that's activation energy. What we mean by activation energy is that these molecules have to run into each other fast enough in order for them to break and form new bonds. Okay, so the minimum amount of energy that these particles have to collide in order to form the product. An example you'll see a lot is if we have a boulder and we're trying to roll it over a hill, we have to push it with at least enough energy for it to then go down to the other side. So if we just push it with a little bit, then it's going to roll back and it's going to stay a reactant. But if we push harder, then we finally get enough energy that it goes over and then it becomes a product. Okay? We see this in energy diagrams. And so here's the potential energy, and then this is just the reaction occurring. So everything is a reactant, and then we have to gain enough energy in order for that collision to happen to reach our activation energy. And usually at that point, energy is released. Not always, but usually. And then that results in our new product. You're going to see a lot of graphs like this. All right, so first part, our reactants, this horizontal line. Potential energy of reactant molecules when they're far away from each other, okay? And then the energy will rise when the separation between them is so small that a collision is starting to happen, okay? So this collision is starting and the energy is increasing. And then we get to a point where we form that activated complex where the reactants are oriented in a perfect way and they have enough energy that they then break the old bonds and form the new bonds. Okay, so that's that peak there. Energy starts decreasing when the new bonds are formed, and then energy falls rapidly to a low value as product molecules separate as they move away from each other. Okay, so let's keep going with our energy diagrams. Okay, so we have this energy diagram. What we saw before was we had our reactants, and then they begin to collide, and the energy goes up, and they have this perfect orientation, and they form the activated complex. And so they break bonds, old bonds, and they form new bonds. And then as those new bonds form, the energy starts to lower, and then as these two new molecules separate from each other, then the energy really drops, and then we have our products. Okay? So, first question, predict. What do you notice about the total energy of the reactants versus the products? Okay? Write it down. Hit pause. What do you think? What do you notice about the total energy? Because what I'm noticing, if our y-axis is energy, the energy of the reactants is much higher than the energy of our final products. And so what type of reaction would this be? Would it be endothermic or exothermic? Okay, well, first let's remind ourselves, what is exothermic and what is endothermic? Exothermic means that we're releasing energy out into the environment, and endothermic means that we're bringing in energy. So if we end with less energy than we started with, that energy had to go somewhere, and so that means it was released out into the environment, so this would be exothermic. Here's another way you can look at this. See our delta symbol again? This means change in enthalpy, change in this energy here. And when we see that, well, delta itself always means final minus initial. So if we take this final energy and we minus it from the initial energy, we're going to have a negative change in this enthalpy, in this energy, right? And when it's a negative change, that means it was released by the reaction. And so that would be an exothermic reaction when this change in energy is negative. So final, and let's just give it some number. Let's say that the products is 5 joules and the reactants start off at 10 joules of energy. So if we take 5 joules and we minus 10 joules, then we end up with a negative 5 joules of energy that was released into the environment. And that's how we lost those 5 joules. Okay, what about this diagram? What do you notice about the total energy of reactants versus products? And would you call this exothermic or endothermic? Okay, go ahead and hit pause, write it down in your notes, and then let's see if you get it right or not. All right, so reactants and products. Reactants have lower energy than the products. And this activation energy is a lot higher than before, and our delta, our change in energy, would be positive because we ended with higher than what we started with. So if we can use our 5 and our 10 again. So if we end with 10 and we started with 5, then final minus initial, final being 10, minus initial, which is 5, we'd have a positive 5. So that means in this situation, with this energy diagram, we had to absorb 5 joules of energy. So if we're absorbing energy, that means that it's endothermic. We brought in energy. Okay. Let's go back to the left slide before. I just want to show you. Activation energy is always where the reactants are starting to how much they have to gain to get over that hill in order to have enough energy to then become products. So notice with this one, the activation energy is quite high because our reactants started off with such low energy. Okay. So, summary. Collision theory, there's 3 parts of this. First, a collision does have to happen in order for new molecules to be formed, for reactants to become products. Not only that, our reactant molecules have to have perfect orientation when they collide in order to form the new products. And they have to hit with enough energy to overcome that minimum activation energy to then become a product. All right, second half. What factors affect reaction rates?